Jai Hind all. This is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College. This is a lecture series on VLSI technology. Its course code is KEC053. We are covering the complex topics, the extra topics that are required for the proper coverage of the main topic lecture series. In the main lecture series, we have discussed all these things from Unit 1 to Unit 5 with the syllabus. And in the today's topic, we will discussing the chapter number 5's complex topic. In the chapter number 5, we are doing the metallization. In the metallization, we have solved all the other steps for the preparation of the wafer. So in a preparation of a wafer, in a preparation of IC, we have first of all prepared the wafer. With the for the wafer preparation, we have prepared EGC, then MGS, from then EGS, then ingot. From there we got the wafers. From the wafers we have grown extra other layers over the wafer, which are the epitaxy layer and the oxidation layer. And with the epitaxy layer and the oxidation layer growth, we have used lithography for the selection of the area where we want to grow epitaxial layer or the oxide layer. Then we have created dielectric and film deposition, which is the same, which is also used for the same epitaxy and the oxidation selections with the lithography. Also, we have used the impurities for the N-type or P-type extrinsic semiconductors, which is done by the diffusion and ion implantation. So with all these steps, we can fabricate a device on a wafer. So this device may be integrated on one single wafer. The different devices that are created that may be integrated on a single wafer. So with this integration, we have to join the different type of the devices that has been created in this whole process. So these devices will be, first thing is joined by the metallization, which I have discussed in the main topics also. Then after that we have packed this VLSI whole structure that we have created. The devices, the ICs that we have created, those are packed with the different type of packaging like DIP, SIP and other type of the packagings. So all these things are the main things that we have discussed in the main lectures. And in the last section, in the last topic, metallization, one topic that we have discussed is that metallization has to be used with some metals, which is mainly aluminium or copper or the alloys. So there are some problems with the use of these materials. In this lecture we will discuss the problems that are created by the metallization and the use of these metals in the metallization. So first thing, metallization, it is a process by which the component of the IC are interconnected by a conductor. As I have discussed that in all the various steps, we use to create a device, and these devices are connected with a connector, and these connectors are conductors generally made up of aluminium. This process produces a thin metal layer that will serve to be like a wire or a conductor between the devices. The pattern of interconnection of the various components on the chip. So these patterns are like the wires between the two different devices. Aluminium is the most commonly used material for the metallization of the mostly ICs. For example, discrete diodes and the transistors that are created on the devices and then to connect these different devices. Then active elements of the ICs are connected by the pattern wiring. These pattern wiring are done through the metallization. So we have to create this wiring which consists of the layer of a metal or polysilicon separated by the insulators. These insulators are usually deposited oxides. So we create different metal devices, and those devices are then connected through the metallization, mainly through the aluminium. So if we discuss the process how metallization is done, first of all we have a device that has been prepared, and we overgrow some thin layer for the wiring of the metallization. So in this process, a layer of oxide is grown over the epitaxial layer or the wafer over the entire piece where we have to grow the wiring. Then the photo etching process removes the oxide area from the desired for the metallization contacts, which is selected through the mask and the photolithography, and these thin films are of metals are applied over this for this contact. Then metal is etched off from the where we do not want. So metal is etched off. After this one, IC may have a multiple metallization layer to reduce the cost. So if we see how it is done, first of all we have created a metallization layer over. If this is the top view of our IC, first thing we will create an IC oxide layer which will be acting as insulator all over this wafer. So an oxide layer is created over the wafer or epitaxial layer. Then over this oxide layer there will be some portion that will be selected for the etching, and in this portion there will be a metal that will be created, and a link is in this area for the metallization. So in this way there is a metal. If there is a two metals over here, let's suppose these are the two metal contacts that are created. So these two metals will be there, and in between there will be insulator which is the oxide layer. So in this way there is a metallization contacts that are applied as a thin film. So basically, to create a metallization or a thin film of metallization, the metal should have different properties. The first property is that it should be a metal, so it should have a low resistivity, so that low resistivity will provide a good contacts, plus there will be no heating due to the resistance. So with the low resistivity, our purpose of the metallization will be more predominantly followed. Then it should be easy to form. We should not be creating any difficulty in the formation. Then easy to etch for the pattern generation, because it will be difficult to etch. The whole device may get spoiled. Then should be soluble with the oxidize, or it should be oxidizable, so that it can be etched properly, and it should be it can have a proper metallization wiring. Then it should have a mechanical stability, mechanical property like mechanical stability, good adherence, as well as the low stress over the in the heating environment, as well as for the lower layers. Lastly, again another thing is that it should have some surface smoothness, because this is the last process, and it should not give stress to the irregularity due to the irregularities to the upper layers and the lower layers. Also for the packaging, other properties are like it should have a stability in the throughout the process. it should not change with the high temperature when we use for the dry and the wet oxidation. So with the high temperature and the dry and the wet oxidation, the process should be smooth and stable. Another thing is that it should have a passivation for the metallization. When we create as oxide, that oxide is also a passivation. So this is again when there is a passivation that may be used with the phosphorus glass or any material for the passivation. So this passivation, there will be no reaction with the metal. So there may be this metal should have a passivation to have no reaction with any metal. For example, as aluminium. So there should be no reaction with metal as aluminium. Lastly, most important is that it should not contaminate our created device, wafer, or any operators that are used for the creation of the wafer. We have done all the previous steps in very clean environment, as we have discussed in the in situ cleaning, as we have discussed the highly contamination free environment. We have discussed the vacuum pumps that give inert gas environment, the ambient control system. All these systems are used so that there should not be any contamination in the device. Now last step is the preparation of metallization. Last step is metallization. So in this metallization, if there is some contamination, all the purpose of the above layers will be not solved. So the first thing is that it should not contaminate the device, even the lower layers, even for the working apparatus, it should not create any contamination. So this will give some merits. Metallization will give some merits. These merits are, first thing is that it will give a conductivity between the different devices. When there is a conductivity between the devices, the whole circuit can work only when there is a conductivity. Second thing, to produce metallized area, the bonding of the wire leads to the packaging of the chip. As we have seen that in the most of the ICs, there is some wires or the legs of the ICs are there that are used to connect to the external circuits. So for example, to connect with an inductor, an IC has to be connected with some inductor. Inductor cannot be created in the IC, so it has to be provided externally. So when it is to be provided externally, we have to connect the internal structure with the external inductor or solenoid. When we are connecting this solenoid to the internal structure, we should have a connection from the IC, from the in between die that is the main devices, to the external device or any component that will be connected through a wire. This wire will give a leg of the die. So these different wires will give the different connections between the external components and the die. These components will be, these wires will be created through the metallization. So it gives metallized area for bonding of the wire leads from the package to the chip, the package that is there to the chip. Lastly, it forms a good mechanical bonds between the circuit and the different components. Metallization gives some problems also. The main problem is irrespective of whatever we use, is that it gives overheating. Whenever there is a movement of the current, it produces heating. So that's why the first requirement that we have, property that we desire, is the low resistivity. As the resistivity will decrease, the temperature will decrease. As the resistivity will increase, the overheating in the IC will be there. So with this overheating, all the properties that we have seen in the main lectures, that will be changing with the temperature. So the limitation of metallization, that when we allow current to pass through the different devices, then there will be a heating that will be produced. So this is a metallization used in the two level ICs. Two level ICs means there are two levels of the devices that are fabricated over the wafer. So in this one, this is, for example, this one is the gates, this is a drain and source and the drain between the different for a MOSFET, and this is a gate oxide over here that is created. A gate oxide is created over here. A gate is this layer. The source and the drains are these ones. Now when this is to be created with the different other material, we have to create contacts. For example, this is again a drain, source and the gate, and when we have to connect this different MOSFETs, we have to use metal contacts. So these are the metal contacts in between these two layers. So these two layers are giving are connected through the contacts. So so this is called a two level metallization scheme, where we have two different devices, one device and the second device, that are connected between with the help of the metallization. The first layer of metal makes contact with the junction in the device. This is the junctions that are in the devices. So this contact are connected through the metals. The second layer of the metal makes contact with the first layer and also with the external circuit. So these are the second layer, this is the second layer, these are the external connections that can be seen over the chip. Now these can given to the external components that are there to be connected externally. So these can be connected with the external circuit. The connections are made by defining trenches called vias. These vias are like this one is a one via between the two contacts. These are separated by dielectrics, which is in between this metallization. So this whole portion is dielectric to be created as insulator between the different contacts. So similarly here we can see this is a metal interconnection that is giving outer outside world external circuits connections. So there are different materials that we can use for the metallization. The first one is aluminium. The aluminium is mainly used as a wiring system. So in this metallization also we use aluminium for wiring. It was since its origin of the IC that aluminium is used as a wiring, pure aluminium. The first circuit that we have seen in the main lectures, first lecture, that was also using the pure aluminium for the fabrication of the wires. Basically this is because of easy preparation as well as for the good conductivity of the aluminium. So the advantage of using aluminium that it can be easily evaporated. So with the easily evaporation due to the low melting point, the silicon, it can have a good adhesion with the silicon oxide. Second is it has good resistance and low resistance. So when low resistance is there, the problem of the metallization, that is the conductivity, heat, will be reduced. So when heat will be reduced, this will be we should have a low contact resistance. So It is lastly, due to its low melting point and easily etchable, it is easy to make pattern with this one. Due to the low melting point, it gives a thermal evaporation which will be easy which will be make easy our purpose of in the lithography. But the problem with aluminium is that it has a low melting point, which is advantage for the some time, but disadvantage is that due to the low melting point, when pure silicon is heated for the other layers, for example, when we create two-layer metallization, for the first layer when we have prepared a metallized layer, thin layer, when we create silicon over that layer to create another layer, then if we use a high temperature process, then due to the low melting point of aluminium, pure aluminium, this will give dissolution of the metallization. So this will lead to dissolve metal into the silicon. So there will be formation of shallow junctions over there. So shallow junctions we have discussed in the main lecture. In the shallow junctions we will have we can create we will have a very junction which is not deep trenches. So this will make short to the different contacts between the in the whole devices. We will see it in the later in the figures also. So when aluminium has a low melting point, it is dissolved into silicon. There are two solutions for this one. One is that we give aluminium some material which do not react with aluminium or the silicon in between the two. So one is that one is to use a barrier metal which do not alloy with silicon and aluminium. So before metallization, if there is a metallization to be done, if this metallization is to done, before that one we have to deploy a barrier metal over here. So when there is a barrier metal, this silicon wafer will not dissolved into the metal. So this barrier metal should not be significantly reduce the conduction through the channel. This is the main property of this metal. This so we have to choose some specifically metals which do not create any hindrance between the channel. These are generally tungsten and the TIN components. So with these two components are first thing are sputtered deposit on the wafer, then we use aluminium to make a contact. The second solution is to give aluminium with some extra silicon in the metal contact. So silicon when added, it is in the 1 to 2%. When this silicon is already added, this will reduce the dissolution of aluminium into the wafer which is already of the silicon. So silicon will move from here to here and it will not reduce minimize the alloying of silicon wafer. Even though this will not completely stops the process, but it will reduce it to the to a high extent. So this is done by the thermal evaporation of aluminium silicon, which work due to the large difference in the melting point of the two elements. So we can use sputtering like electron beam evaporation to make these composition of the contacts. So with the aluminium, the other possible ways we can use the alloys in between the aluminium and silicon, or we can use aluminium with the silicon. The third is the third part. So So there is a different alloys that we are used. One is that we use aluminium, where we use aluminium. When aluminium is used, only aluminium is pure aluminium is used. So this is pure aluminium. When pure aluminium is used, it may be dissolved into the wafer. So this is wafer, this is metal, and this is maybe an oxide layer. So wherever there is opening, it will go into the silicon to make a contact. So excess alloy leads to the melting of the aluminium. Second is, if we use a slide formation, means if we use aluminium with the silicon, then this aluminium that is there, slide is there, which is aluminium and silicon alloy. When it is created, this will be giving a shallow junction over here, which is the one solution. Second solution is to create a barrier metal. So if we give a barrier metal over here, the hashed portion, a barrier metal is prevent reaction to be overgrown of the aluminium into the wafer. Secondly, it will this metal is of TiN or some W metals, tungsten metals. So this will solve our problems with the aluminium. The other third possible condition, third possible way of metallization is using aluminium or copper alloys. For aluminium of copper nucleus, this is required because of the high integration. When with the increase in the device integration, we need to decrease the thickness of the metal layers, because with the decrease in the thickness layers, we can thickness of the metal layers, we can increase the number of epitaxial layers. So when we decrease the thickness of the aluminium metals, this will lead to migration of electrons between the layers. This is because the thin films with an electric field gradient due to the applied voltage also develop a thermal gradient due to the resistance of the heating. That's why the main problem with metallization is heating. The thermal gradient is high for the thinner layers, because the thinner layer will have different gradient in the upper and the lower layers. So this difference will be high. So this is there is a higher thinner thermal gradient. So this will reduce their resistance is high. So this cause local heating and migration of the metal from thinner area of the wire. So when this will be the electron will move from one layer to the another layer, there is a connection between the two different layers. So with these connections, with this electromigration, there may be open circuit for the metallization. So to reduce this aluminium's electromigration, generally we add copper to a very small extent, 0.505 to 4% of copper is added. This alloy that is formed between the copper and aluminium forms a copper aluminium precipitates, which is called GP ions. These precipitates spins the grain boundaries and reduce the electromigration. So this is similar to the silicon addition, but here the precipitation is there. So this precipitation will reduce the dissolution of silicon into the aluminium. So generally what we use alloy metal with aluminium, silicon and copper, where aluminium is the main metal and silicon is used for 1 to 0.5%, and then copper is used for 4%, maximum of the 4% in the alloy. The fourth possible way is use of the pure copper. The main problem with aluminum copper alloy is that it has a high resistance. Since with this high resistance, the pure copper has to be replaced aluminum so that the metallization can be produced and there may be proper conductance. So this was used where the deposition of the thermal deposition by the thermal evaporation can be done. By more importantly, it can be evaporated on the wafer. So this will decrease not only the cost but also the vacuum in the chamber that is not to be needed. But the problem with this one is that we have to diffuse into silicon and the silicon oxides. This can when it goes into the deep, this can destroy our device. So we have to take care in the front end of the line as well as the back end of the line for the separation of the two metals. So this is all about this different devices, different metals that we are used, and the problems of the aluminium to be used. All the topics that we have covered in this one are from the SEZ's book. Here we are going to end this lecture series. Thank you.